Welcome to a special edition of AI Unraveled. It is December 20, 2025, and the rules of physics and business have just been rewritten. For 30 years, quantum computing has been stuck behind a single, insurmountable wall. The more qubits you added, the more the system fell apart. That era ends today. We are breaking down Google's historic unveiling of the Willow processor, a chip that doesn't just manage errors, but suppresses them exponentially as it scales. But this isn't just a hardware story. We're uncovering how DeepMind's AlphaQubit AI is the invisible brain, keeping these quantum systems stable, why Moderna and DHL are already placing their bets, and why the Harvest Now, Decrypt Later threat means your current data security might already be obsolete. The quantum era isn't coming, it's here. Let's unravel the breakthrough.
Welcome to the deep dive. For, 3 decades, the biggest challenge in quantum computing felt like a kind of cruel scientific joke.
It really did.
The theory promised this, exponential power, but the physics was just brutal. Every time you added a component to make it more powerful.
It just got more fragile. The whole thing would just fall apart. The engineering could never live up to the beauty of the math.
But that's what we're here to talk about, because that paradox has finally been flipped on its head. We are now officially leaving the world of pure physics and, really, entering the era of scalable quantum engineering.
A huge moment.
Today we're doing a deep dive into Google's Willow processor and the algorithm that runs on it, quantum echoes.
And we're going to break this down for you into 3, I think, really critical areas. First, how scientists finally got hard experimental proof that quantum error correction not only works, but scales exponentially.
Then how that stability lets us move past these abstract goals, like supremacy, towards something called verifiable advantage on real problems.
And finally, the 2 massive consequences this creates. The immediate security threat of Harvest Now, Decrypt Later, and the huge physical barrier on the horizon.
The energy wall. Okay, so let's start with the basics. Just enough so you can really get your head around the scale of what they've achieved here.
To really appreciate what Willow is, you have to remember why quantum is so different. It all starts with a concept called quantization.
And the best analogy for that is?
A staircase. In our world, the classical world, things are continuous, like a ramp. But in the quantum realm, everything's discrete. It's like steps. An electron can be on step 1 or step 2, but never in between. That idea that granularity is fundamental.
Which leads us to the qubit, the quantum bit.
Right. A classical bit is a switch.
Yeah.
Off or on, 0 or 1. But a qubit uses superposition, so it's a mix of both 0 and 1 at the same time. Think of it less like a coin spinning in the air and more like a wave function that holds all the possibilities at once.
You mentioned the scale. So with Willow's 105 qubits, how does that actually translate into speed?
Well, this is where it gets mind-bending. The power is exponential. With 105 qubits, you have 2 to the power of 105 possible states, all existing simultaneously.
Which is a number, that is.
It's bigger than the estimated number of atoms in the entire visible universe. That's the state space you're working with. That's the source of the speed-up.
But you need all those qubits to be able to talk to each other,
Right.
To work together.
And that's entanglement. Einstein's spooky action at a distance is this invisible link where the fate of one particle is instantly tied to another, no matter how far apart they are. In a processor, entanglement is the wiring. It lets you affect the whole system by touching just one part.
Okay, so we have this incredibly powerful system, all wired up with entanglement, but it's been historically just tragically fragile.
Because of decoherence. The second the quantum state touches the noisy outside world, it collapses. Poof. All the information is gone.
And you can't just make backup copies like you do with a normal computer.
Exactly. The no-cloning theorem. You can't copy an unknown quantum state. That was the wall. For 30 years, that was the wall.
So let's talk about the hammer they built to break that wall. The Willow chip uses an architecture called the surface code. And the key is that not all the qubits are doing the same job.
Correct. You have your data qubits, which, hold the actual information you care about. But then scattered among them, you have what are called measure qubits, or stabilizer qubits.
Their job is to be the lookouts.
Like silent alarms. They check on their neighbors. But here's the brilliant part. They check the parity of their neighbors, which is basically just seeing if an odd or even number of errors has happened without actually looking at the data itself, so they don't cause a collapse.
So the thing we call a stable, error-corrected logical qubit isn't one physical thing. It's a team effort. A whole grid of physical qubits, maybe a 3x3 or 5x5 grid, all working to protect one piece of information.
Yes, and this is the breakthrough. proving that making that team bigger actually makes it exponentially better.
This is the aha moment, the experiment.
The Google team built logical qubits of different sizes.
Yeah.
So using different code distances, they called them distance 3, distance 5, distance 7, and they compared the error rates.
And the result was staggering. Exponential error suppression every time they added more physical qubits to protect the logical one.
Every single time. The error rate for that logical qubit dropped. And not just by a little, but by a consistent factor of about 2.14.
And that number, 2.14, that's the smoking gun.
That's the signature we've been waiting decades to see. It's the proof. Adding more parts doesn't make the system more fragile. It makes it exponentially more stable. The physics problem is, for the most part, solved.
Okay, but a stable chip is only half the battle. You need an equally smart system to manage it in real time, which is where the AI comes in. AlphaQubit.
Right, AlphaQubit. It's a neural network from DeepMind. The problem was that older error correction algorithms, they were too rigid. They couldn't handle the weird, specific kinds of noise you get in a real chip, like crosstalk or leakage.
So this AI basically becomes an expert on this one specific chip.
It learns the chip's noise personality. It's like a custom-trained repair system that's far more accurate than the old methods. Now, we should say there's still a bottleneck.
The delay.
Yeah, the decoder takes about 50 to 100 microseconds to run. That's a delay they'll need to shrink for really, really big calculations.
But the big takeaway here is that the future is hybrid. It's the quantum chip running ice cold and a massive classical AI brain running right alongside it, keeping it honest.
Absolutely.
So stability is solved. Now, what can we actually do with it? We all remember the term quantum supremacy, which, let's be honest, had some pushback. Critics said it was an abstract calculation with no real use.
And that's fair. So the goalposts have moved. The new standard is Verifiable Quantum Advantage.
And they showed this with the quantum echoes algorithm. It calculates something with a very dense name, out-of-time order correlators, OTOCs.
The name is a mouthful, I know. But the idea behind it is actually beautiful. It's basically a way to measure the quantum butterfly effect.
How fast chaos spreads through a system.
Exactly. You let a system evolve forward in time, you give it a tiny little nudge, a perturbation, and then you mathematically run the clock backward.
And the more chaotic the system is, the less it looks like the original when you reverse it. The echo of the original state fades faster.
And that rate of decay tells you incredibly important things about the material you're simulating. They use this for a really powerful application in chemistry. They call it the molecular ruler.
Right, because in drug discovery, one of the hardest problems is figuring out the exact 3D shape of a complex molecule, the distance between the atoms.
A classically impossible problem for large molecules. But Willow, running this algorithm, could infer those distances with incredible precision. And the benchmark is just stunning.
It performed the calculation 13,000 times faster than the world's best supercomputers.
And this is the key. It's verifiable. The output isn't some abstract number. It's a physical property like magnetization that you can go and check against real-world lab equipment, like an NMR machine. It's a tool that gives you the right answer.
And that result has lit a fire under the entire industry. We're seeing this huge push for quantum readiness on, a 3 to 5 year timeline?
Oh, at least. Biotech is first in line. Drug development fails so often because we can't properly simulate the quantum behavior of molecules. A quantum computer is the natural tool to simulate a quantum system.
This is the Moderna partnership. They're using these algorithms to simulate mRNA folding, to screen new drugs entirely on a computer in silico instead of in a lab.
Then you have logistics. Think of companies like DHL or FedEx. They're using quantum optimization algorithms, specifically one called QAOA for route planning. Even a tiny improvement in efficiency, what they call dynamic network recalibration, saves millions in fuel and cuts emissions massively.
Don't forget finance, the ability to run these massive Monte Carlo simulations for risk analysis almost in real time instead of overnight. That's a game changer.
The commercial applications are just exploding, but that 13,000x speed up, it cuts both ways. We had to talk about the dark side of this power, the security threat.
The existential threat. Willow's success just pulled the timeline forward for the scariest application of all, breaking modern encryption.
We're talking, of course, about Shor's algorithm, the one that can factor large numbers exponentially fast, which is the mathematical problem that underpins almost all of our public key cryptography. RSA, ECC, all of it.
Which brings us to the acronym HNDL, Harvest now, decrypt later. Explain what that is.
HNDL is a simple, terrifying strategy. Adversaries, state-level actors, are vacuuming up and storing huge amounts of encrypted data today. They can't read it now. But they're betting that once a cryptographically relevant quantum computer, a CRQC, comes online,
Which they expect between 2028 and 2035.
they can just decrypt everything they've saved. It means any data with a shelf life of more than 5 or 10 years, military secrets, corporate IP, medical records, is already compromised.
That's a 5-alarm fire for security agencies. So what's the fix? What's the countermeasure?
The global response is the NIST PQC standardization. NIST has been running a competition to develop new encryption algorithms that are resistant to quantum attacks. They just finalized the first 3 standards.
ML-Chem for keys, and then LDSA and SLHDSA for signatures.
Exactly. These are the new building blocks. And the mandate is out. Corporations and government agencies have to find all their old crypto and migrate to these new standards. The deadline is 2028. Willow just made that deadline feel very, very real.
So we have the quantum computer, and we have the race to deploy quantum-safe crypto, but there's a huge physical problem looming over all of this.
The ultimate bottleneck, the energy wall.
People forget this part. These chips, like Willow, have to be kept colder than deep space. That takes enormous dilution refrigerators. But the cooling isn't even the biggest power draw.
No, it's the classical computers you need right next to them. The control electronics and, of course, the giant AI decoder, AlphaQubit. That all takes a colossal amount of electricity.
And this demand is hitting at the exact same time as the explosion in energy needed for training large language models.
It's a perfect storm. The U.S. Department of Energy put out a warning. They project that by 2030, 25% of all new energy demand in the country will come from data centers. Our grid, our aging electrical grid, it just can't handle that.
So if you can't rely on the public grid, the answer is to build your own.
You bypass it entirely. That's the idea behind the ASE-PAC Energy Corridor. It's being talked about as a Manhattan Project-level effort to build dedicated power spines, think next-gen nuclear plants, or massive renewable farms wired directly into these new compute clusters.
And the implication of that is just profound. The whole geography of the digital economy is about to change. Data centers used to be built near cities for low latency.
Now they'll be built near gigawatt-scale power sources. Computational supremacy will literally follow the energy.
Okay, this is all transformative, but let's ground ourselves for a minute. We have to end by looking at the remaining hurdles, the critiques that are still out there.
And there are 2 big ones. The first is what you could call the fragility critique. Yes, the error correction works. But the physical qubits themselves aren't that much more stable. The coherence time for a qubit in Willow is still only about 68 microseconds.
Vanishingly short.
It's an eternity in quantum terms, but it's still tiny. So skeptics say we're still firmly in the anti-skew era noisy intermediate scale quantum. The counter-argument, of course, is that the exponential scaling proves it doesn't matter. The math works even with noisy parts.
Which leads right into the second problem. The overhead problem.
The surface code, for all its power, is incredibly inefficient. The estimates are that to break standard RSA 2048 encryption, you'd need a machine with about 20 million physical qubits.
And Willow has 105.
Right. So going from 100 to 20 million, that's a manufacturing and engineering challenge on a scale that is hard to comprehend. Most of your machine is just working to keep a few logical qubits alive.
But if we pull back and synthesize all of this, the ground has fundamentally shifted. The question is no longer, is fault-tolerant quantum computing possible? We know it is.
The question is now an engineering one. Can we build it big enough, fast enough? And can we power it?
So the landscape for 2028 is clear. It's these 2 massive races happening at the same time. Everyone's scrambling to migrate their security to PQC, and this global competition to build the energy infrastructure to power the next generation of computing.
That's it in a nutshell.
So, a final thought for you to take away from all this. We now know that the exponential suppression of quantum errors works. The science is sound. So if the main barrier is no longer physics, but purely engineering and industry scaling up manufacturing, cryogenics, and power, does the future of computational supremacy rest less on who has the most brilliant algorithms and more on who can build the massive power infrastructure first? Something to think about as the lights start to flicker.
That brings us to the end of this special briefing. The takeaway is stark. We have moved from the question of is it possible to can we build it big enough? The Google Willow result is a signal that the timeline has compressed. By 2028, quantum readiness won't be a buzzword. It will be a compliance requirement for every Fortune 500 company. Whether you are in logistics, pharma, or finance, the time to audit your cryptographic vulnerabilities and your energy strategy is now. Stop reading reports. Start leading with insight. If you need to align your executive team on these shifts without the noise, we build custom 5-minute AI-powered audio briefings tailored for your C-suite. Secure your strategic podcast consultation today by emailing us at info@jamgatech.com or clicking the link in the show notes. Until next time, keep unraveling the future.